So last time we talked about speed of wave in a string. Okay, so speed of wave in a string. So let's go back to this question. So last time we talked about the speed of wave in a string depends on tension of the string. Greater the tension, faster the wave travels. Okay. So tension affects the speed of the wave, and also it depends on the thickness. Okay, this is the mass per unit length, how thick the string is. So speed is inversely proportional to square of mu. Mu is again so mu is mass over length. Okay, mass per unit length. So today we will talk about a little bit about speed of sound. Okay, we don't need to worry about the formula for speed of sound. Okay, that's a little bit complicated, so we will not deal with that. But we'll just talk it qualitatively. Okay, so speed of sound depends on two things. The first one is it depends on temperature. Okay, so what do you guys think? Is the speed of sound directly proportional or indirectly, or meaning if you increase the temperature, will that increase the speed of sound, or will that decrease the speed of sound? Increase. That's right. So why is that? So as you increase the temperature, that increases the speed. Why increasing the temperature increases the speed of sound? The reason is, as you increase the temperature, the air molecules, okay, you need medium to transfer sound from one point to another point. Okay, so for any sound to travel through a medium, you need to disturb the medium. Okay, so when there is higher temperature, the molecules are already jiggling. Okay, so they are moving at higher speed. So that contributes to the faster propagation of wave. So as you increase the temperature, the molecules starts to jiggle faster. As a consequence, the wave is also propagated quicker or faster. So that's why speed of sound depends on the temperature directly. At room temperature, the speed of sound is about 343 meters per second. Okay, we'll use this number for room temperature. But again, as you increase the temperature, the speed also increases. The other thing that affects the speed of sound is the molecular mass of the gas in atmosphere. Okay, larger the molecules in the air, less is the speed. Okay, because bigger molecules have greater inertia, so it takes more pressure to jiggle the molecules. So sound travels slower in the medium that has bigger molecules, bigger air molecules. Or in other words, smaller the air molecules, faster sound travels to the medium. Okay? This last sentence is basically telling you that the speed of sound at room temperature is faster than speed of sound in room temperature. Helium is faster than speed of sound in room temperature. Helium is faster than that in room temperature air, because helium has less molecular mass, okay, than the molecules in air. One more thing I haven't mentioned here. The other thing is, it also depends on the state of the material or medium. For example, speed of sound in solid is faster than the speed of sound in liquid. Okay? Speed of sound in liquid is faster than the speed of sound in air. So if you compare the speed of sound through the solid versus speed of sound through air, you will see that sound travels much faster through the solid because the molecules are close, right? So they can easily transfer their energy to the adjacent molecules. Whereas in air molecules, the molecules are pretty far apart, so it takes some time to transfer the energy. So sound travels faster in more compact structure. So again, sound travels faster in solid compared to liquid, and sound travels faster in liquid compared to air. So these are some of the speed of sound at different medium. So if you see speed of sound in solid, these are all solid medium, much higher than speed of sound in liquid, okay? And speed of sound in liquid is higher than speed of sound in air. Okay? So more compact the material, faster the sound travels. Again, it's due to the closeness of the molecules, because they can easily transfer the wave to the adjacent particles. Okay, so that's about the waves, qualitative description of waves. Now we'll talk about representation of waves. Okay, so we have two types of representation of waves. One is graphical representation, and the other one is mathematical representation. So first we'll talk about graphical representation. Okay? So there are two ways to represent a wave, a traveling wave. The first one is something called snapshot. Okay? So let's say there is a wave traveling. Okay? There's a wave traveling to the right. And again, this is only the wave, not the medium. Okay? So you have a medium here. The medium itself is not traveling or propagating. What is traveling here is the wave. The medium can go up and down. It can go up and down, but it doesn't get displaced. It remains as at its original location. Okay, so this is the wave, some kind of wave that is traveling to the right. Okay, and this picture is the wave at some specific time. Okay, some specific time t1. So as if you are you are taking pictures. Okay, so you started taking picture. So this is the picture you took at t1. Okay, and now you take another picture. Oops. So you take another picture delta t time later. So this is at t1. And now delta t time later, it will be displaced slightly to the right. Okay. In the same manner, you can take multiple pictures. Okay. So this is delta t later, and in another delta t later, you can take another picture. In another delta t later, you can take another picture. So you can take many pictures, and each of the pictures that you take at a specific time is called snapshot. Okay, so this is one kind of representation. So snapshot is the picture of a wave at a specific time. And you see that although the wave is traveling to the right, you see the shape of the wave does not change. The shape of the wave remains same. Okay? It's just displaced to the right. Okay. And snapshot is basically, it gives you the shape of the wave. Okay. So in other words, as you move towards x-axis, it tells you how the height is changing. So if you look at this point, that's the height of the wave. If you move to this point, that's the height of that wave. Okay? At that point, that's the height. That point, that's the height. So it tells you how the height of the wave changes with the position. So this is again another snapshot at some other time, t3. It's moving to the right. And again, this is very important. I want to remind this again and again. It's not the medium that is being displaced here. Okay? So what is being displaced here is the wave. The medium here is a string or something. It remains at its original location. The wave, the medium goes up and down, but the position of the medium remains as it is. It doesn't move forward. Now, one thing you can see clearly here is when the wave hits this point. Okay, so this. Let's say that this is a string, a piece of string, and this piece of string has many molecules. Okay, there are many molecules, small molecules. When the wave hits this part, this gets lifted up. Okay, so the height of the molecule being displaced up would be exactly the same as the height of the wave. If this is the height of the wave, then this molecule, the molecule of this part, will be lifted up to that point. The molecule here would be lifted up to that point. Okay? So the molecule in the medium is displaced to the height that is equal to the height of the wave. Okay. Now there is another kind of representation which is called histogram. Okay, so the first one we talked is snapshot graph. Now the second one is histogram. Histogram is basically, it tells you how the particles in the medium is moving up and down with the time. As the time passes, how the molecule is moving up and down. So for example, so usually histogram is the graph of a single molecule or a single particle in the medium. Okay, so we'll focus on this single particle that is located at x1. So this is the string, okay, and we will keep our eyes at this location. At this location, that's the height of the particle, because I said that before. The displacement of this particle would be same as the height of the wave. Okay? At this point, the wave has that much height, so the particle would be displaced that much. Okay? So this is at time t1. Okay? So that at time t1, that's the displacement of the particle. And again, we are keeping our eyes only at that point. Only we are focusing at this point. And then at the later time t2, that's the height of this particle. Okay? This particle is being lifted further up. Initially it's here, now it's lifted further up because the wave is going towards the left, sorry, to the right. So that's the location of the particle at later time. At time t3, that's the height. Okay? At t4, that's the height of the same particle. It's the same particle. Okay, same particle that is located at x1. But what we are looking at is how it is being displaced up and down at different times. Okay, so this kind of graph is called histograph. So histograph is that it tells you how the particle, single particle, moves as the wave passes through it. So usually, if the wave is traveling from left to right, so here in this case, wave is traveling from left to right, the histograph is just the reflection of or image of inverse image of the snapshot graph. Okay? So you see here, this is just the opposite of this one. Okay? It's like you flip this, you get that. That's usually true in case of the wave traveling to the right. If it is traveling to the left, then you will get the same graph. We'll practice some of that in homework. Now let's look at some example that will show you how you convert from snapshot graph to histograph. Okay, so here's an example. So we have this snapshot graph. Again, this is the graph at some specific time. In this case, the time is 0 second. Okay, so at 0 second, this is the graph of some wave. Now we want to, and this graph is traveling at 1 meters per second. Okay, so this is traveling to the right like this. It's going to the right at 1 meters per second. And we want to convert this histograph, this snapshot graph to a histograph. And we also need to know at which point we want to focus. Okay? Do we want to focus at 1, 2, 3? So that would be given in the question. So in this case, we'll focus on, let's see, so that's traveling to the right. So we want to find a histograph at 3 centimeters. Okay, so here, we'll keep our eyes at this point. So we'll focus at this molecule. So as this wave hits this molecule, how the molecule move up and down. So in the first second, how much distance will this wave travel? It's moving at 1 meters per second. So how much distance will it travel in 1 second? So we want to know during this time, from 0 to 1 second, what would be the displacement. So for that, we need to know where this wave will be in 1 second time. So how much distance will it travel in 1 second?
1 meter.
1 meter, exactly. It's a kinematics problem, right? You did that in physics 1. Let's see. So we know that velocity is distance over time, and distance is velocity times time. Okay, so velocity is 1 meters per second, 1 meter per second, and time is 1. So 1 times 1 is 1. So it would be displaced by 1 meter. That means this part would be at 3. Okay, so this whole thing would be shifted 1 meters to the right. So it will be shifted here. Now, between this time, 0 time, and 1, see here, let's go back. Between 0 and 1, it travels from here to here. Okay? And when it's traveling from here to here, between 0 to 1 second time, nothing happened at 3. Because the wave is still here. Okay? So nothing happened. Nothing happened until it hits 1 second. Okay? So there's nothing here. Because we didn't see anything until the end of the 1 second time. And at 1 second time, the particle here will move down, because we know that the displacement of the particle is same as the height of the wave. The height of the wave is that. Okay? So the particle would be moved down, same as the height of the wave. And now in the next second, again, it will be displaced 1 meter to the right. So this whole thing would be 1 meter to the right there. And as the wave is moving from 3 to 4, that is from 1 second to 2 second time, it's 1 second to 2 second time, you see that that's the height at 3 seconds, and this remains the same. Okay, height remains the same from 3 to 4 seconds. So we have the same height. So same height from 1 second time to 2 second time. And again, we are keeping our eyes here. Okay, so the wave is we are looking at this point as the wave is moving to the right. So when the wave moves from this point to that point, we see that the height is always constant between these times. Okay, so height is constant. Now as soon as it hits 2 seconds, what happens? So at 2 seconds, it immediately jumps from that point to that point. Okay? And then it moves to the right again. Okay, so between 2 seconds and 3 seconds, what happens? You will see this part, and then this part will be displaced, and you will see next part and will be displaced, and you will see that part. Okay, you are keeping eyes at that point, and then you will see that part. Okay, so at the end of 3 seconds, your height would be that. Okay, the height of the particle here will be that. So the height is decreasing. And again, in the next second, from 3 to 4, it will be decreasing. Okay, so the height will be decreasing. So what you see here would be that the height is decreasing. So that's the histogram from snapshot graph. Again, this tells you how the particle is moving up and down, whereas this one is how the wave is moving to the right or to the left. Another example. So here's a snapshot graph. It's moving at 1 meters per second to the right. And we want to draw a history graph at this point. Okay, so we want to keep our eyes fixed at 4 meters location. So in 1 second time, this would be the location of the wave. And again, let's go back. So it travels from here to here during 1 second. Okay, so from 0 to 1, nothing happens. Okay, nothing happens. So when the wave is going this way, it doesn't. You don't see anything here until it reaches 1 second. At 1 second time, okay, 1 second time, you will start seeing this graph, this part. So as it moves further to the right, you will start seeing these other points. Okay, so you'll see these points. So you'll see increase in the height. Okay, so you'll see increase in the height. And when it goes further to the right, now at 4, it's decreasing, right? So you'll see decreasing part. And again, you see this one is just a reflection, inverse reflection of this one. It's like if you flip this, see, take the mirror image of that, you get that. Okay. So here is a question. So this is a snapshot graph, and these are also snapshot graphs. So you need to decide where would this wave be after or at negative 1 second time. So this is at 1 second time. So at negative 1 second time, where was the graph? So think about that. So this graph is moving to the right. That means you need to go back in time. Negative 1 second means you are going back in time. So it travels, in 1 second period, it travels 1 meter. So at 0, you need to go 1 meter to the back. And from 0 to negative 1, you need to go 1 more meter. So which one is the right one? No right one?
B.
Huh? B? This one?
Yes.
So, wait. This is at 1 second. Okay? At 0, this would be at 0 because this would be displaced to the left by 1 meter when the time is 0. Now you need to displace 1 more meter to the left for -1. Right? So let's say here is my location at 1 second time. At 0 second time, my location will be here. -1, it will be here. Okay? So we need to go back. So then we need to go to the left by 2 meters. That means you can just choose any reference here. So let's say this one. So you need to move, this is at 0, so move this to -2, that would be your wave. So which one is there? So that's one, that's A. So let's look at this one. So this is the snapshot graph. So I want to get, this is history graph. So I want to get history graph from snapshot graph. So which one is the history graph? And it's at this point. We are keeping our eyes at that point.
Is it A?
B?
D.
D? Why do you think it's D? Why is it D?
Isn't it the inverse?
Inverse, but not along this axis. Inverse along this vertical axis. So here.
Oh.
So this is the inverse along this this vertical axis, not horizontal. So that's a very important thing. That's one way to think about it. Another way is, so between this point, between, let's say, this 0 time and 1 second, it travels that much. Okay, nothing happens. And then in the next part, you will see this part. So that would be the displacement of the medium, okay? Which is not this one, because it's displaced in positive direction, which is not this one. It's not displaced in negative direction. So displacement is that, okay, in that much time. Not that one. So we are considering that much time. So displacement in that much time is that. So this is not the one. In that much time, that's the displacement, okay, which is what we see here. So one thing you can think about here is which one is leading edge and which one is trailing edge. So this one is the leading edge. Okay. So as the time starts, this is the leading edge. This starts in the beginning, and this is the trailing edge that comes in the end. So first one, this comes, and then that, and then that. Okay. So this point is that point is that point is that, and then next, okay? Because this is the leading edge, that's why you see this one to be flipped when you change it to history graph. Okay. So that's the answer. Okay. Sinusoidal waves are common types of waves in which the particles in the medium move in periodic fashion. You guys learned about simple harmonic motion in physics 1. You guys remember what is simple harmonic motion? Simple harmonic motion. Any kind of motion in which the object moves forward, back again to the other side, and then back again, and then this way, and then back again. So when the particle moves to and fro, or back and forth, all the time, that kind of motion is simple harmonic motion. Okay? It could be a pendulum, it could be some kind of musical instrument, okay? It could be water wave, so different kinds of waves. They all are sinusoidal waves. Or they are all simple harmonic motion, and the wave formed by those kinds of motion, simple harmonic motion, is sinusoidal waves. Okay? So sinusoidal waves are produced by the source that oscillate with simple harmonic motion. Okay? So any kind of periodic motion is simple harmonic motion. Periodic means you start from a point and then you go somewhere and then you come back again, and then you again go to the same path and come back again. Go through the same path and come back again. That's the periodic motion. Any kind of periodic motion could be called simple harmonic motion. There is another technical definition, but I'm just using here a very basic layman definition. Okay. And this is the wave you usually see in simple harmonic motion. Okay, this is called sinusoidal wave, because this is sine function or cosine function. Mathematically, this is sine or cosine function. That's why it's called sinusoidal wave. So you may remember that this is the amplitude. The highest point in this wave is the amplitude. Okay? How much it is displaced. For example, I started here. This is my equilibrium position, and I'm displaced up to this point. Okay, so I'm walking, and displaced up to this point. So this is from my starting point to this point is the amplitude, highest displacement. I don't go further than this. So this is my highest displacement. And also on the left side, I go up to this point, same amount of distance. So that's my amplitude. So amplitude is the maximum displacement from equilibrium. Okay, in wave, so this is just a representation of different kinds of motion. So this could be sound wave, this could be some kind of like wavy thing, or wave on a string. This is just a representation. Okay, so this is the maximum height or maximum displacement. That's the maximum displacement. That's the maximum displacement. So basically, if I want to match this with my motion, so this is equilibrium. Okay, this is equilibrium. Initially, I am at the maximum displacement. So I start not from here. This is although this is my initial position, but I start my motion from this point. Okay, this is the maximum. So that's my maximum amplitude. So I'm starting from here. Now I go to equilibrium. I go to my equilibrium here, and then I go to the negative maximum. Okay, I go to this point. That's the negative maximum, and then I go back to my equilibrium here, and then go to positive maximum here. Okay, that's that, and then go back to equilibrium here, and then go to negative. So that's the representation of my back and forth motion. So likewise, you can also represent motion of the pendulum. Okay, so this is a pendulum, let's say. So that's the maximum displacement of pendulum. So that's that. Okay, and then the pendulum goes down. So that's equilibrium, that, and then this way, that's that, and then back to equilibrium, and then back to maximum. So this kind of motion, back and forth motion, is also simple harmonic motion, which is represented by this sinusoidal wave. Okay. So this positive maximum is called crest, okay, and the negative maximum is called trough, which is denoted by A. A is maximum distance or displacement. Negative A is the negative maximum displacement. And then, like simple harmonic motion, the sinusoidal waves are repetitive. Okay, repetitive means like you start from here. So you start from here, goes up, back, and this repeats all the time. Okay, so that's the repetition of simple harmonic motion. Same kind of thing here. This is one complete cycle, and in the next cycle you get the same pattern, same wave. In the next cycle you get the same wave. So that repeats all the time. Okay, so just like repetition of the sinusoidal motion or simple harmonic motion, the waves also repeat all the time. And the distance between the peak to peak, okay, from the maximum displacement, one maximum displacement, to another maximum displacement, or from one crest, this is called crest, to another crest, this is called wavelength. Okay, you might have seen this in physics 1, but if not, so this would be this would be new thing for you. So distance from one crest to another crest, any to adjacent crest is called a wavelength. Okay. Now, so if you look at, let's say this wave is a snapshot picture. Snapshot picture, you guys know what is snapshot picture, right? Snapshot picture is the picture at one specific time. Okay, so focus on this one. This is at one particular time. So if you look at this wave, how is the height of this wave changing? What factor determines the height? How is the height changing? Or what variable affects the height of the wave? Or this is my location, okay? So how much I'm going to move, what my displacement would be, depends on what? My displacement to the right depends on what thing? It depends on how far I am from my original location, right? If I move to this much, then that's my displacement. If I move here, that's my displacement. So displacement depends on where you are, okay, or position. So if you are looking at a snapshot graph, your displacement tells you what your height would be, or what your displacement would be. Sorry, if your position tells you what your displacement would be. Okay. So, for example, here at this position, that's your displacement. At this position, there is no displacement. You are sitting at equilibrium. At this position, that's your displacement. At this position, that's your displacement. So, how much displacement is there in the wave? That depends on the position, where you look at. Okay? And if it is a history graph, let's say you have, I didn't bring a pen. Let me bring a pen.
Why do I take this class?
Do you need it?
For grad school, yes. I majored now.
Yeah. I did the same way.
My brain's not ready for this.
Okay, so you have this curve or a wave, okay, and it is traveling at some speed v. Okay, so at some time t later, that wave would be here. Okay, so you're watching this wave traveling to the right. Okay, you're standing here. So what will determine the height of this wave? This wave would be here, on some other location. At time t, we focus at, let's say, you are looking at this point. Okay? So that's your eye. Okay? So initially, the wave starts from here, and the wave is traveling to the right. Okay? Now, the height of the wave, it depends on what? It depends on time. Okay? Time. So, at different times, the height will be different for histogram. Okay? For snapshot graph, it depends on x. Okay? So, the displacement of this graph depends on both time as well as the location. Okay? Where you are located, as well as at what time you see the graph. If you see the graph at, you don't even need to do that, so you can just look at, you just look at this one, okay? Easier one. Your eye is somewhere here, okay? You're looking at this point. So this wave is moving to the right. So at t1, this is the height. Okay? Now it is shifted a little bit to the right because it's moving to the right. So it's shifted like this. Okay? And now that's the height. Okay? At some time t2. So this is at t1. Now it's moving further to the right, so now at this point that would be your height. That would be the height of the wave. Okay? And then this would be the height. So you see the height is changing, right? At different times. So the height of the wave, or the displacement of the wave, depends on time. Okay? So displacement, that's called d. It depends on time. If it is a moving wave, if it is a traveling wave. If it is a snapshot, so snapshot, it depends on x, location. So whether you are looking at this point, or this point, or this point, that tells you how high is the wave. So at this point, x1, that's the height. At x2, that's the height. At x3, that's the height. Okay? So you see, this depends on both time as well as position, depending on what type of wave is that. If it is a traveling wave, it depends on t. If it is a snapshot still picture, it depends on x. Okay? So let me just fast forward. So this is for constant. This is for constant time. I'll come back to that again. So that's the representation of a sinusoidal wave. Okay? Sinusoidal wave is a sine wave. Sine wave means it could be sine or cosine. It's same thing. Okay, so if you guys don't remember the graph of sine, so if you plot sine theta, it will look like this. Okay, that's the sine theta. If you plot cosine, that will look like this. They are both same. Okay, it's only displaced by that much. Okay, if you shift this origin here, then it becomes, this is cosine. Then cosine, sine becomes cosine. Okay, if you shift cosine a little bit to the left, okay, a little bit to the left, then it becomes sine. Okay, sine and cosine are both same kind of function. Only difference is that much part, which is called phase difference. Okay. So whenever you come across a sine wave, you can either represent the sine wave by cosine or sine. Both are fine. it could be represented by either cosine or sine. Sometimes you may see sine, okay? So don't be confused. It's still this wavy thing, okay? If you see sine here, it's still same thing. Only difference is that small part. Okay, if it is cosine, you start from this maximum point, okay? So this maximum height. If it is sine, you start the wave from this equilibrium. Okay, so for example, if I start from here, if I start my motion from here, this is the starting point. I represent this by sine, okay, because I'm starting from equilibrium. So that's sine. If I start from here, okay, then this is cosine. So depending on where you start, it is sine or cosine, but both are same kind of wave. Okay. Now, so this shows that the displacement, like I said here, displacement, this y is the displacement, how big is the wave at particular location. It depends on both x as well as t. Okay. Now, if the wave is moving to the right, then we have a negative sign here. If the wave is moving to the left, we have a positive sign here. Okay, so the positive and negative determines which way it is moving. So why it is positive here? Now think about the traveling wave. Okay, so wave traveling to the right. So you have a wave traveling to the right. Okay. Let's say you are keeping your eye at some point here, at this point, and this is traveling to the right. Okay. Now, as it travels to the right, because you are keeping your eye at this point, so the height needs to be same. Okay. This y needs to be same. Right? Because we are focusing at this point. That's the height, okay? This is y, displacement. You can focus at any other point if you want. You can focus at that point or any other point, that's fine. I'm focusing at that point, and that's y. And as it moves forward, I'm keeping the eyes at that point all the time. That means this needs to be constant. Okay? But as it moves to the right, x is changing, right? So it moves to the right. So here, that's x. Now it moves to the right, that means that's x2 or x plus delta x. So there is increase in the delta x or increase in x or position. So you cannot keep this constant, height constant, by changing x. Your x is changing as you move to the right, but your height is same. You're looking at that point. So by changing x, you cannot keep this constant. That means you need to compensate that increase. So the way to compensate that is by adding this term. So as it's moving to the right, the time is also increasing, right? So initially, that's at, let's say, 0 second, and then it will move to the right at 1 second, and then move to the further right at 2 seconds. So there is increase in time. Okay? So there is increase in time, and there is also increase in x. So they compensate each other, keeping this y constant. So both x and y, x and t are changing or increasing. When x goes up, when t goes up, x also goes up by the same kind of amount, and that keeps y constant. Now, if the wave is moving to the right or to the left, so this is moving to the right. Now, the wave is moving to the left. It's moving to the left. So as you go to the left, t is increasing, okay? Because there's no negative time, so You start at t equal to 0 and then move to the left, so t equal to 1, and then t equal to 2. So t is increasing as this wave moves to the left. But when you go to the left, x becomes more and more negative. Okay, so here x is negative 2, x is negative 1, x is 0, x is 1. So x becomes more and more negative. So when you go to the left, sorry, this becomes more and more negative. Okay, and this becomes positive. That means to compensate the increase in time, you need positive number here. If you put negative sign here, what will happen? Both will increase. Okay, so you will get negative time and negative x. So this will, as you increase x, the time will also increase, and that will give you different y. So y will not be constant. So to keep y constant, you need a positive sign here, because this is always positive. To compensate the increase in time as the time passes, you need a positive sign here, because this is negative. Okay, the sign of x is negative. Okay, I think we are out of time, so a little bit over the time. I will post the video of this one. If you didn't understand anything, you can watch the video again. There is no homework this week, but starting from next week, we will have lots of homework and also lots of classwork. So this will go a little bit faster from next week. If you have any questions, please feel free to email me. And have a great weekend. And please wipe your chairs with the sanitary wipe.